2. Introduction. Measurement of time series components means to identify the components, isolate the components, and eliminate the components. The components of time series like seasonal, cyclic, and irregular has already been discussed in other modules. One can visit the module, Introduction to the Time Series and its Importance, to recall about the components of time series. In this module, our main concern is, if one can detect the components of time series in the data, then what to do next. One must apply some methods to measure or eliminate them. Hence, in this module, measurement methods for seasonal, cyclic, and irregular components are discussed one by one. In this module, first we will discuss methods of measurement for seasonal variation. As seasonal is a component of time series that prevails for a short time period, so most of measurement methods for seasonality can only be applied on the data whose values are available after a short time periods like monthly, quarterly, etc. 4. Statistical applications in environmental sciences. In continuation, we will discuss about the methods for the measurement of cyclic variations. As cyclic variation can only be observed on a long period data, hence it is generally evaluated by eliminating other components from the time series. Last component of time series is irregular variation, and it is generally considered as an error term or residual term that cannot be completely removed from the data. In the next session, methods for the measurement of different components will be discussed in steps. As lot of mathematical calculations are required to find out these values, thus one should be aware of basic terms like sum, average, proportion, etc. 3. Measurement of seasonal variation. Seasonal variation occurs due to seasonal factors and man-made effects on the variable in any time series. There are many methods available in the literature for the measurement of the seasonal variation. Some of the most useful and important methods are: 1. Method of simple average. 2. Ratio to trend method. 3. Ratio to moving average method. 4. Link relative method. Let us discuss these methods in details. 3.1 Method of simple average. This is the easiest and simplest method to measure the seasonal variations. To find out the simple average, one has to follow the steps. Steps for calculating seasonal variation indices are: filled circle, arrange the observations in quarterly, monthly, yearly manner according to the requirement of study variable or availability of the data. Calculate the average values of observations for all quarters, months, years over different years. Now calculate the quarterly, monthly, yearly, seasonal average values. To find out average of quarterly, monthly values, divide total of quarterly, monthly values by 4/12 to get seasonal average values respectively. Seasonal average equals total of the season with respect to 1 year number of the partition in a season. 5. Statistical applications in environmental sciences. Filled circle, calculate seasonal indices for different years by expressing quarterly, monthly, seasonal average as percentage of total average of quarterly, monthly, seasonal. Seasonal index for ith year equals seasonal average. Total of the seasonal average times 100. Filled circle, note that total of seasonal indices for quarter must be equal to 4*100, i.e. 400, and for months, it must be 12*100, i.e. 1200. Filled circle, note that seasonal here represents quarter or month. There are 4 quarter and 12 months in a year. Next, we will discuss an example of sales of bicycle to compute the seasonal indices using simple average method. Example 1. Sale of bicycles in lakh from year 2012-2017 are given in the table 1. Compute the seasonal indices using method of simple average, hypothetical data. Year, second, quart, third, 6. Statistical applications in environmental sciences. Statistical applications in environmental sciences. First, arrange the quarters data corresponding to year. As in 2012 year, first quarter, second quarter, third quarter, and fourth quarter values are given as 14, 10, 16, and 12 respectively. Similarly, we also have values for 2013, 2014, 2015, 2016, and 2017 years. Now calculate seasonal average for all year using formula for calculating seasonal average. Seasonal average for 2012 equals 14 plus 10 plus 16 plus 12, 4 equals 13. Also calculate the same for 2013, 2014, 2015, 2016, and 2017. Total average for each quarter is calculated by using formula total average for first 14 plus 12 plus 10 plus 3 plus 10 plus. Similarly, calculate the same for other quarters. Now compute the seasonal indices by given formula for calculating seasonal indices in method. Seasonal indices for 2012 equals 13/10. Now calculate total of seasonal indices by summing all seasonal indices for 2012, 2013, 0.2017. It is equal to approximate 600. We know that for quarterly data total of seasonal indices must be 400. So there is need to do adjustment in them. To do adjustment in seasonal indices, multiply seasonal indices by correction factor k. K equals 400. Total of seasonal indices. K equals 400, 600 equals 0.6666. Adjusted seasonal indices for 2012 equals 124.799 times 0.6666 equals 83.1991. Similarly calculate for 2013, 2014, 2017. Now, calculate total of adjusted seasonal indices, and this total is equal to 399.96 approximately. 4. This This method is based on the assumption that data doesn't contain any trend and cyclic component. The major important factor by using this method is that a regular component eliminates by averaging seasonal indices that can be quarterly or monthly. This assumption is not really true in economic sector, hence this method can't be used in all sectors in an efficient manner. 3.2 Ratio to trend method. Ratio to trend method is an improvement over the method of simple average. To calculate the seasonal indices by this method, one has to follow some steps. These steps are: filled circle, firstly calculate the trend value by least square method. Method of least square was already discussed in the module, measurement of secular trend. Filled circle, then denote the data as a percentage of trend values. Filled circle, assuming that the multiplicative model of the time series fits the data, then this modified data contains seasonal, cyclic and irregular components. For removing the cyclic and irregular components, one has to take average for all quarters months separately. Filled circle, now the total of seasonal indices should be 1200 for months and 400 for quarters. If this is not the case, then there is need to do some modification in the seasonal indices by multiplying it with constant k. K equals 1200. Total of seasonal indices, k equals 400. Total of seasonal indices for monthly and quarterly respectively. 8. Statistical applications in environmental sciences. Three. Statistical applications in environmental sciences. Module 38. Introduction to Stationary Time Series. Learning objectives. Introduction. The aim of this module is to give a basic introduction about stationary and non-stationary time series and understand its concepts and significance. We will discuss its properties as well as try to explain its importance in other areas. In this modules, examples are added to help students in understanding the topic in an easy manner. 2. Introduction. Time series analysis has wide application in the practical world. Then the questions that comes to the mind are: what is the purpose of using this tool? Why time series analysis is considered as the most important tool in the financial field? How this analytical tool is considered as more useful than any other methods? Many of these types of questions will be in your mind. We will try our best to answer all these types of questions in this model. We studied about the time series and how to measure its components in the module, Introduction to Time Series and its importance. We are rewriting here again about time series. What is time series? Time series is the sequence of observations that record the data at regular time intervals such as retail price index. The main purpose of using this analysis is for the description of the data, the construction of the models which fits the data, forecasting future value. 4. Statistical applications in environmental sciences. Let's say a business analysts want to analyze the future situation of the company. First step is to analyze the previous year's figures so that using those figures they will be able to comment on it. Here the analysis has been done with time-dependent data. Another example is that predicted weather predates the monsoon prediction in the year 2018. For this, she has used the analysis of previously recorded data and has concluded about the status of monsoon. In the most practical situation, observation data relies on time. In these situations, time series analysis is more useful. Linear regression analysis is also used in forecasting, but it is less useful because it considers the relationship of one variable with other variables such as hours spent in a day for study correlated with the mark score or yield of crop depends on other factor, etc. The main thing in regression analysis is that here observation values may not be observed with time, but in time series observations are observed with time. Therefore, it is important to understand the relationship of variable over time. For example, the price of share increase or decrease with time. Here the weather condition on a particular day depends on its previous day weather. Hence it is important that one should study the relationship of a variable with its previous values through modeling that not only helps in the fitting of the data in more appropriate manner but also for future predictions. Time series analysis is used to understand the behavior of any variable over time. Time series analysis consists of different techniques, theory and methods to predict the future value based on previous observed value. This prediction theory is therefore classified as time series forecasting. This analysis is used from ancient time period to present time period. In ancient time, people has used their own knowledge to predict future value such as weather prediction by looking at the weather condition of the sky. Time series analysis and forecasting has wide applications in different areas. Time series analysis is mostly used in business and economic area. Some other applications areas are weather forecasting, pattern recognition, earthquake prediction, mathematical finance, etc. 3. Time series is stochastic process. A time series is a stochastic process because time series is a sequence of observations, and sequence of observations is basically a realization of sequence of ordered random variables, i.e. stochastic processes. A brief about stochastic processes is given here so that one can understand it. Definition. Stochastic process is families of random variables which are function of, say, time. A stochastic process is also known as random process or random function. It is denoted as yn is greater than or equal to 1, where yn is a random variable at time n. Basically, it is a sequence of random variables that model the value of process at time n. 5. Statistical applications in environmental sciences. Definition. A time series process is a stochastic process indexed in discrete time and continuous state space. For example, daily closing price of share market. Such series can be written as YTT equals 1, 2, 3. 4. Stationary time series. In general terms, stationary means stability. In time series analysis, stationary means stability of the stochastic process with respect to its random variable. It means there is no changes in the time series with respect to changes in the time interval. This is known as stationary time series. In literature, there are two types of stationary. These are a. Strictly stationary. B. Weakly stationary. 4.1 Strictly stationary definition. A stochastic process is said to be stationary or strictly stationary times if joint distribution of YT1, YT2, YTN and YT plus K1, YT plus K2, YT plus Kn are identical for all T1, Tn and K plus T1, K plus Tn and J and all integers n. This means that all statistical properties remain constant as time elapses, i.e. mean, variance and covariance of the process remain constant. A white noise series is stationary series with mean 0 and variance sigma 2. 6. Statistical applications in environmental sciences. Figure 1. If the graphical representation of any time series is same as the above shown image, this time series is known as stationary time series. Although it is not a good method to check about the stationary of any data, one has to use the properties to test about the stationary of the data. Example. Let UT be the independently and identically distributed standard normal random variable. Show whether the following process is stationary time series or not. PT equals cos WT plus UT. Solution. As UT is independent and identically distributed standard normal random variable, i.e. covariance term is 0. Also, E UT equals 0. B UT equals 1. To show stationary time series, statistical properties must be constant, i.e. mean and covariance must be a constant value. Cos WT plus UT equals cos WT cos UT minus sin WT sin UTE cos WT plus UT equals E cos WT cos UT minus sin WT sin UTE cos WT plus UT equals 0. 7. Statistical applications in environmental sciences. Also COVPT, PS equals 0. Hence one can observe that the mean and covariance values are constant. So given series is said to be a stationary time series. Also, it is difficult that all the time series must satisfy all the conditions of the strictly stationary. For example, it is difficult in general that variance remain constant over time. So in general, second type of stationary is mostly used due to its flexible nature. 4.2. Weakly stationary time series. A stationary or strict stationary condition does not hold in real life because it is not necessary that all properties are constant with time. So to overcome the problems of strictly stationary, another type, weakly stationary time series, is introduced. Definition. A weakly stationary time series requires that mean and variance of the process remains unchanged as time elapses, but covariance depend on its time difference, i.e. lag. Such that COV-YS, YT equals E-YS, E-YS YT, E-YT. Where YS, YT are the random variable that model the value of process at time S and T respectively. This covariance depends on lag or time difference, i.e. T minus S, if T greater than S. Now in the following section, we will discuss some properties of time series that help in modeling the data. These properties help in deciding the model to fit the data. Example. Let UT be the independently and identically distributed standard normal random variable. Show whether the following process is stationary time series or not. Also check that it satisfies the properties of weakly stationary process. PT equals UT minus 1 plus UT. Solution. For stationary process, mean and covariance should be same. PT equals E UT minus 1 plus UT equals 0 COV PT. PT plus K equals COV UT minus 1 plus UT. UT plus K minus 1 plus UT plus K. COV PT. PT equals COV UT minus 1 plus UT. UT minus 1 plus UT. Equals COV UT minus 1. UT minus 1 plus 2 COV UT. UT minus 1 plus COV UT. UT. Equals var UT minus 1 plus var UT equals 2. 8. Statistical applications in environmental sciences. Time series has constant mean and covariance change as time difference change. This covariance value at lag 0 is 2. Now, find covariance value for one lag, it is 1. Covariance value for lag greater than 2 will be 0. So, one can see that as time interval changes, covariance value changes, i.e. covariance depends on the lag or time difference. Thus, this process is the weakly stationary time series. Here, we can see that the mean is 0 and covariance term is not same for all lag, basically it is a function of time lag. Hence we can say that the process is not strictly stationary but it is weakly stationary. 5. Definitions. A autocovariance function. The covariance between any pair of elements of same variable of a stationary sequence depends on its lag difference. This covariance is known as autocovariance. The autocovariance function gamma k element of z of a stationary process's y is defined as follows. Gamma k equals COV YT, YT plus k, gamma k equals E YT YT plus k, minus E YT E YT plus k. Gamma k equals gamma minus k if k equals 0, autocovariance converts into simple variance, i.e. Gamma 0 equals var YT equals sigma 2 in the stationary process. The means are constant and covariance are function of time lag. Therefore, the covariance between two variables remain same, have same lag, i.e. time difference. Hence, in the autocovariance function, there is no need to mention about the starting time, but it is necessary to mention time lag k. On the other hand, if a process is non-stationary, then the autocovariance function depend on two variable. First is time t and second one is lag k. It means that covariance of variable changes with time although having same lag. Then the notation for the autocovariance is denoted as gamma t, k equals COV yt plus k. Here gamma t, k denotes the covariance between yt and yt plus k for a non-stationary time series. B. Autocorrelation function, ACF, the autocovariance function defined on squared units, so it depends on absolute size of measurements. We can make it independent of the absolute size of yn by defining a dimensionless quantity, the autocorrelation function. The autocorrelation function for a stationary series defined as rho k equals core yt plus k equals gamma k, gamma 0, rho k equals rho minus k, where rho k is called the autocorrelation function, ACF, with lag k. 9. Statistical applications in environmental sciences. The ACF of a purely indeterministic process satisfies rho k right pointing arrow 0 is k right pointing arrow infinity. It means that as we increase the time lag between variable, then the autocorrelation between the variables converge to 0, i.e. no relationship. If the process is not stationary, then we have the different notation for autocorrelation like autocovariance. The autocorrelation function for a non-stationary series defined as rho t, k equals COV yt plus k, square root var yt plus k, where t is the time period and k is the lag value. See parallelogram. Autocorrelation function is the most commonly used method to study the relationship between variable at different time period in time series. One can derive a lot of information about a time series from a plot of a sample autocorrelation function on one axis and lag on the other. This type of plot is named as parallelogram. D. Partial autocorrelation function, PACF. It is an important characteristic of a stationary series. Partial autocorrelation function is the conditional correlation of yt plus k with yt given yt plus k. Yt plus k minus 1. It means that in the partial autocorrelation function is the autocorrelation between two variables by fixing the values of other variables. PACF can only be defined for positive lags. The values of the partial autocorrelation function may be derived as the coefficient empty set k in the following equation. Min e yt minus empty set k, 1 yt minus. According to this principle, always consider the model with smallest possible number of parameters to be selected for representing an adequate time series data. Out of most suitable models, select simplest one because complicated model has large number of parameters. Large number of parameters shows overfitting of model. Overfitting is not suitable for future forecasting. So for future forecasting of time series model, we select most parsimonious model among all the possibilities. 10. Statistical applications in environmental sciences. 6. Types of stochastic model. Basic introductory time series model, multiplicative and additive model, contain error term in terms of a regular component, but this component is not random. Error term must be considered as a random quantity because variations in real-life problems are random. Thus, by adding an error term in the time series model, the basic model of time series is turned into stochastic time series model. The selection of a proper model is extremely important as it reflects the underlying structure of the series, and this fitted model in turn is used for future forecasting. These stochastic models are based on the assumption that corresponding time series must be stationary time series. In general, time series data can have many forms. Different stochastic process models are used to fit the data. These are some linear time series model that is mostly used in literature. These models can only be used with stationary time series, such as autoregressive model AR. Autoregressive model explains the current value of a random variable, say yt is a linear combination of its past values with additionally externally generated random variation. For example, current price of a commodity is based on the previous prices of the commodity. ARP model for a random variable yt defined as yt equals mu plus n array summation alpha I yt minus I minus mu plus et. P I equals 1, where mu is the constant value. Alpha I, s are autoregressive coefficient. Et is the white noise process with mean 0 and variance sigma 2, et tilde n 0, sigma 2. If P equals 1, then autoregressive model of order P known as first order autoregressive model. It is denoted as AR1. This is a simplest form of autoregressive model of order 1. AR1 is defined as yt equals mu plus alpha yt minus 1 minus mu plus et. After substituting the value of yt minus 1, then yt minus 2. And so on until y0. Then we get yt equals mu plus alpha t y0 minus mu plus n array summation alpha j. T minus 1. J equals O. Et minus j. 11. Statistical applications in time series analysis requires computer awareness because it involves long and hard mathematical calculations. These type of calculations cannot be solved by hand for a long time. There are some statistical software available to solve this calculation. Some of these are eViews, R, SPSS, SAS, Python, Excel. The most useful software is eViews and R. R is user-friendly and free software available. It is very easy to use this software. There are lots of content available on the internet. 2. Introduction. In practical cases, the data of time series are available in the raw form. That means one cannot apply the time series tools and techniques on them in direct manner. In most of the cases, data of time series are far away from stationary. In original time series, there are many types of fluctuations available like variability and mean, variability and variance, volatility and relation with other variables. Forecasting of respective time series cannot be done in the presence of these fluctuations. If forecasting will be done with fluctuations, mean variance of the forecasted values will fluctuate. Thus stationary time series is considered a standard time series for forecasting because mean and variance value of the forecast values remain same as the original time series, that is, there is no change or significant difference on the mean and variance values as time passes. One can use this stationary series to make better forecasting of the series. Hence stationary process is the essential condition for accurate forecasting. If time series is non-stationary, then one need to remove non-stationarity factors from the series and convert it into stationary process. 4. Statistical applications in environmental sciences. Let us suppose a case of asset prices in the share or property market. As asset prices are recorded at a particular time period, recorded prices fluctuate over time, which means there is no stability in various statistical characteristics of the object like mean and variance. If we are interested in the prediction of the future asset value, then predicted future asset value will not be accurate and reliable due to instability in the characteristics of the prices, that is measures through statistical properties such as mean, variance and covariance of the recorded data. It means statistical properties are not constant, it varies over time. From previous module, Introduction to Stationary Time Series, if statistical properties are constant over time, respective data are known as stationary data and the process is known as stationary process. If stationarity condition doesn't hold either strong or weak, then the process is considered as a non-stationary. One can also use the term non-stationarity for this type of the process. Definition. If the statistical properties of the recorded data are changing over time, that means mean and variance are not constant. Recorded data is known as non-stationary data and process is known as non-stationary process or non-stationary time series. This type of non-stationarity condition is mostly seen in financial and economics field as financial market shows either increasing and decreasing trend or fluctuations in the market. This is among the best example to understand non-stationarity. Now let us define the behavior of the non-stationary time series. 3. Behavior of non-stationary time series. In this section, some most important key features will be discussed about behavior of non-stationary, such as if the graphical representation of the recorded data shows upward or downward trend, cycles, random walks with without combination of trend, cycle and random walks, then time series is non-stationary data and have non-stationarity condition. 5. Statistical applications in environmental sciences. In the following figure, one can see the different components and their combinations that exits among different time series through different colors for better understanding. Figure 1. The terms like random walk, etc. will be discussed further for better understanding of the concept in the module. Non-stationary data possess non-stability into the mean and variance in long run. This means that variance goes to infinity as time goes infinite and mean value never becomes stable on one value as time passes. Non-stationary data can't be predicted, modeled and forecasted due to presence of non-stability factors that lead to variation in the values of statistical properties like mean, variance over time. To get consistent and reliable outcome of non-stationary data, there is a need to transform non-stationary data into stationary data. Under stationarity condition, forecasted value will be consistent and reliable. 4. Types of non-stationary processes. Before discussing the transformation of the non-stationary time series into stationary time series, different types of non-stationary process will be discussed. These non-stationary process may be helpful in the transformation of the non-stationary process. Some well-known non-stationary processes are random walk without drift, random walk with drift, deterministic trend. 6. Statistical applications in environmental sciences. 4.1 Random walk. In simple term, random walk is a sequence of random changes, either in the variable or process, subject to condition. Random walk is also defined as a path taken by a point and quantity that moves in steps, and direction of each step will be decided randomly. Suppose you want to predict chances of accident of a drunk who is walking on road. One truck is coming towards him and he is walking randomly. He is in the middle of the road now and truck is coming towards him. He takes steps randomly left, right, forward or backward from the current position. You can't predict if that person will meet with an accident because he is taking steps randomly in random direction. Drunk person taking moves step by step randomly, so this process is known as random walk. Now let us discuss statistical definition of the random walk in statistical terms. Random walk is a stochastic process consisting of a sequence of changes in stepwise manner, each of which step characteristic is determined by chance or randomly. Random walk theory is mostly used in stock prices and exchange rates. Random walk is discussed in two ways in the literature. One is random walk without drift and other is random walk with drift. Random walk without drift. Random walk without drift simply is a random walk in which today's stock price will be equal to yesterday's stock price plus a random stock. This is a non-mean reverting process, which means that it can move towards positive and negative side and variance changes as time changes in long run, so that it can't be predicted. Mathematical expression for random walk without drift is PT equals PT minus 1 plus UT, where PT is the price of the stock at time t. PT minus 1 is the price of the stock at time t minus 1. UT is the variable that take positive or negative value. 7. Statistical applications in environmental sciences. Here the price of the stock at time t will depend on the price of the stock at time t minus 1 and the random movement of the stock price at time t. Random walk with drift. Random walk with drift. Tomorrow's value will be equal to the today's value plus drift plus random variable. Drift is the constant and average value of measuring changes. It can be used to measure trend, cycle. It is not accurately predictable because there is no constant mean and variance. Mathematical expression for the random walk with drift. PT equals beta plus PT minus 1 plus UT, where PT is the price of the stock at time t. Beta is the constant parameter. PT minus 1 is the price of the stock at time t minus 1. UT is the variable that take positive or negative value. Here the price of the stock at time t depends on the average value of the stock plus price of the stock at time t minus 1 and random movement at time t. Now in the next section, we will discuss about the techniques that can be used to remove non-stationarity from the data. 5. Techniques to remove non-stationarity. Non-stationary means lack of stationarity, in other words, the absence of stationarity or stability of statistical properties in the data. Lack of stationarity is caused by the presence of non-stationary factors like deterministic trend, deterministic cycle, etc. It is important to detect these factors at the initial stage so that after removing these factors one can apply statistical methods to forecast prospective values for the original time series. This section will introduce the techniques for detecting non-stationarity factor. There are many techniques available in the literature of time series analysis. 8. Statistical applications in environmental sciences. Some of them are discussed in the module. One can refer to the literature for in-depth knowledge of these methods. 5.1. Least square method for elimination of trend. Least square trend method is used to measure trend component. Basically, the purpose of measurement of component technique is to first identify the components, then isolate it and eliminate from the data if possible. As some of the components like irregular variation or random term is difficult to eliminate completely from the data or series. There are many methods like moving average method, method of semi-average that are available in the literature, but least square method is the best method among the all methods to eliminate trend. Actually, a time series cannot remove overall trend. A time series will always keep some trend value. But least square method removes trend as possible as it can. Least square method is the simplest and widely used method because of its unbiasedness. Detailed procedure of this method is described in the module, Measurement of Secular Trend. One can refer this module for mathematical formulation of the method. Least square method removes all type of trend like linear trend, quadratic trend, curvilinear trend and exponential trend, etc. 5.2. Differencing unit root test. Before future forecasting of a time series, respective time series should be stationary time series. Since stationary time series have constant mean and variance in the long run. Forecasting is very important feature of a time series. Most of the time series show variability in original data. They are not applicable to forecast future value. There is a need to transform non-stationary data into stationary data. Merely stationary time series provides better and consistent result to any recorded data due to stability prevails in the statistical properties. In literature, there are many methods available to transform the non-stationary process into stationary process. But differencing is very important method for transformation. Differencing method is also known as unit root test. Differencing is a method to detrend the recorded data. In this method, difference of variables are taken. This difference is taken on the basis of the characteristic of the recorded data. Suppose there is a random process PT. The first difference of a series PT is given as increment PT equals PT minus 1. 9. Statistical applications in environmental sciences. If, after taking first differencing, the process will fulfill the requirements for the stationarity, then the transformed process derived from the original process is stationary time series, and original process or time series is called integrated to order 1 and denoted by I1. If the first differencing does not fulfill the requirements of the stationarity, then there is a need to take second differencing by the equation. Increment PT equals increment 2 PT equals increment PT minus 1. If the second difference follows stationarity properties, then second difference is stationary but not the original time series. Then the original series is considered as integrated of order 2 and denoted as I2. If a process difference d times in order to induce stationarity, the series is called integrated of order d and denoted by ID. One can see that still process is non-stationary but their difference is stationary. 5.3. Seasonal differencing. If time series is affected by seasonal factors and man-made factor, time series has seasonal variation. Seasonal variation shows short-term movement in the time series like daily, hourly, weekly, monthly, quarterly but less than a year. There are many methods discussed in the module, measurement of seasonal, cyclic and irregular variation, to measure seasonal, cyclic and irregular components. There is one more method to eliminate seasonal variation from the respective time series. This method is known as seasonal differencing. Seasonal differencing is based on the season factor. If time series is affected by monthly seasonal factors, seasonal differencing will be taken on 12 period. In that case, differencing is done in fractions rather than integers. Similarly, this can happen for other season factors. Now we will discuss a case where monthly seasonal differencing are taken. For example, let us consider that the time series PT records the monthly average temperature in India. A model is of the form. Opening parenthesis. 10. Statistical applications in environmental sciences. PT equals alpha plus beta t plus ut. Where alpha is the constant parameter value, beta t is the periodic function with period 12, ut is a stationary time series. Then the seasonal difference of PT can be defined as nabla 12 PT equals PT minus 12. Equals alpha plus beta t plus ut minus alpha plus beta t minus 12 plus ut minus 12 equals ut minus 12. One can see that this seasonal difference is stationary. So one can say that after seasonal difference, series can be reconstructed. Now after taking the seasonal difference, the transformed series is stationary. 5.4. Method of moving average. Method of moving average is used to measure trend component. Moving average method are also used to eliminate periodic variation from the time series. Method of moving average have some loss of information from the given time series. This method is very simple and based on the sum period. This period decide on the basis of time series movement. Number of cycles defines the period of moving average period. Moving average method is discussed in Measurement of Secular Trend in detail. One can refer these modules for detail learning. 6. Stochastic time series process. After addressing a non-stationary time series to stationary time series, next step is to fit a model on the respective time series. Many time series stochastic models are used to fit a transform time series. Most widely used and important stochastic models are discussed here. These are autoregressive integrated moving average and integrated moving average model. 6.1. Autoregressive integrated moving average process ARIMA. An autoregressive integrated moving average process can be denoted as ARIMA P, D, Q. When time series is non-stationary, we can't directly apply ARMA P, Q of that series. Thus first we have to convert non-stationary series to stationary series by taking differencing. 11. Statistical applications in environmental sciences. After differencing d times we will get series that fulfill the requirement of stationarity, then we can apply ARMA P, Q model on the differenced series, and the original model is known as ARIMA P, D, Q model. Where P is the number of lags of the dependent variable AR terms. D is the number of differences required to take in order to make the series a stationary. Q is the number of lags of the error term MA terms. 6.2. Integrated moving average model. An integrated moving average model can be represented as EMA D, Q. An integrated moving average is simply an ARIMA model with P equals 0. That is, the EMA D, Q model is the same as the ARIMA 0, D, Q. The EMA D, Q is a moving average which has been integrated d times. Here, we will study the simplest case, the EMA 1, 1 also known as ARIMA 0, 1, 1. The model can be written as CT minus ZT minus 1 equals ET minus AT minus 1, where a lies between minus 1 and 1 because of the invariability condition. Since D equals 1, the series ZT is non-stationary. Example. Let us consider an example of quarterly data for the Consumer Price Index CPI and Gross Domestic Product GDP of the UK company. Here, this time series will be used to check non-stationarity. If it is non-stationary, then convert it into stationarity, and to find appropriate stochastic model. Solution. Here, we are using eView software to solve this example. To check non-stationarity in the time series, steps are given below. To see the characteristic of the time series, the first step is to plot the data. One can see from figure 2, first figure top left, that represents the plot of the data. This shows a deterministic trend in the data. So, this time series is non-stationary time series. 12. Statistical applications in environmental sciences. The second step is to transform the non-stationary into stationary time series by differencing and plot it. Figure 2, second figure top right, shows the plot of differencing time series. From this figure, one can see that difference time series is stationary time series. One can take log to smooth the time series. Log time series shows non-stationary and difference of it is stationary time series. Figure 2. To find the order of stochastic time series model. To find order of time series model, plot the ACF and PACF values, i.e. correlagram for the difference log time series. Figure 3 shows that PACF values rapidly decline to 0 after 1 spike and ACF values rapidly decline to 0 after 5 spikes. According to correlagram, ARMA model is fitted with AR1 and MA5. Figure 3. 13. Statistical applications in environmental sciences. So possible model or ARMA 1, 1 ARMA 1, 2 ARMA 1, 3 ARMA 1, 4 ARMA 1, 5. Estimation of ARMA model. Now, estimate all the possible model for the time series and choose appropriate one. ARMA 1, 1 ARMA 1, 2. Figure 4, a figure 4b ARMA 1, 3 ARMA 1, 4 figure 4c figure 4d. 14. Statistical applications in environmental sciences. ARMA 1, 5. Figure 4e. In figures 4 of minus 4e, coefficient column shows parameters value like alpha, beta, theta for all ARMA. ARMA model are discussed in detail with mathematical equations in the module, Introductions to Stationary Time Series. Probability column shows whether parameter is significant or not. Parameter is significant if probability values is less than 0.05, otherwise not. Here, significant means that parametric value is acceptable. Adjusted R-square means how much data is fitted by the model. In other words, how much model is successful in explaining the variation of the data. As the value of adjusted R-square is close to 1, result of all possible ARMA model. Table 1 shows the combine result of all possible ARMA model. From all these model, we have to choose one of the best and appropriate model. The term degree of freedom is used in the table. It means independent observations that are included in the respective model. 15. Statistical applications in environmental sciences. ARMA 1. ARMA 1, 5 and ARMA 1, 4 are the most appropriate model among other model, because their adjusted R-squared value is greater than all other possible time series model, i.e. 0.218 and 0.23. Since ARMA 1, 5 is not appropriate model because MA5 is not significant. MA5 is not significant because it is less than 0.05. One can check this by fitting the MA5 model on the data using the eView software. Thus, ARMA 1, 4 is the most appropriate one as it has AG. R2 is higher than all model. It satisfies the stationary condition, so one can conclude that ARMA 1, 4 is the parsimonious model for GDP data of UK company. 7. Summary. By studying this module, one can get knowledge about non-stationary time series. Behavior of non-stationary time series is discussed. Some of the non-stationary models like random walk with drift, random walk without drift are discussed. Definitions and notations are also given for better. 16. Statistical applications in environmental sciences. Understanding. Examples of non-stationary time series, techniques to remove non-stationarity factors, stochastic time series model for non-stationary time series are discussed. In this module, In this module, ARIMA models with different order are discussed and how to choose the best model is discussed. The best model is further used to forecast future values. This future forecasting can be done by using Box-Jenkins methodology. This methodology will be discussed in the module, Box-Jenkins methodology. This mathematical model was designed in 1970 by two developer George Box and Gwalem Jenkins, who proposed in their book, Time Series Analysis, Forecasting and Control, to identify, estimate, forecast and diagnose a standard statistical model for a specific and particular time series data. The mathematical model is defined in the textbooks as Box-Jenkins methodology because it is developed by two mathematicians Box and Jenkins. Box-Jenkins method is a widely used process to find out the best model for a time series data. In this module, we will define the Box-Jenkins method and tips for using it for a time series data. 3. Box-Jenkins method. Box-Jenkins method is based on the assumption that the time series process can be approximated by ARIMA stochastic time series model if the given time series is stationary. Also, time series can be approximated by ARIMA stochastic time series model if the given time series is non-stationary. Box-Jenkins method is a three-stage method aimed at selecting a parsimonious ARIMA and ARIMA model. 4. Statistical applications in environmental sciences. For the purpose of estimating and forecasting a univariate time series, Box-Jenkins method referred as stochastic and iterative process to select a standard statistical model. The three stages are 1. Identification. 2. Parameter estimation. 3. Diagnostic checking. If the identified model passes the diagnostic tests, then model is ready to go for forecasting. If it does not, the diagnostic tests indicate model ought to be modified, and a new cycle of identification and diagnostics is performed. It will continue till identified model pass diagnostic test. It is an iterative process. Let's discuss these steps of Box-Jenkins methodology. 3.1 Identification. Identification step is used to check if the given time data is either stationary or non-stationary time series and to find order of parameter for autoregressive and moving average term. According to this, identification are classified in two classes. I. To check whether time series is either stationary or non-stationary. If time series is stationary, next step is to identify the parameter of the standard statistical ARIMA model. If time series is non-stationary, convert it into stationary series or remove the non-stationarity factors. There are many techniques available in the literature to remove non-stationarity factor. Some of the techniques were discussed in the module, Introduction to Non-Stationary Time Series Model. Let us discuss it again for better understanding. If particular time series data shows deterministic trend, it can be removed by least square trend method. If particular time series shows seasonal variation in the data, it can be removed by method of seasonal difference. If particular time series shows periodic variation in the data, it can be removed by the method of moving average. 5. Statistical applications in environmental sciences. One of the most used method to transform non-stationary to stationary is differencing or unit root test. In unit root test, one takes the difference of the process until difference process becomes stationary. E. Identify the parameter of the standard stochastic time series model ARIMA. Once stationarity has been addressed, the next step is to identify the order of parameter of autoregressive AR and moving average MA terms. The order of the parameter can be identified by correlagram of autocorrelation function ACF and partial autocorrelation function PACF values. Mostly time series data is non-stationary in real-life data. So, ARIMA is mostly used to fit time series model. An ARIMA P, D, Q model is completely identified by the choice of non-negative integer value for the parameters P, D and Q. Parameter value P can be found by ACF and PACF. PACF values cut off to 0 after some spike of correlogram, ACF decrease exponentially towards 0. This cutoff lag value is the order of autoregressive term IEP. Parameter value Q can be found by autocorrelation ACF and partial autocorrelation function PACF. ACF values cut off to 0 after some spike of correlogram, PACF decrease exponentially towards 0. This cutoff lag value is the order of moving average term IEQ. Parameter D is the number of times differencing the time series. The following principles can be used to choose the appropriate value of D. A time series can be modeled by stationary ARIMA model if the ACF decays rapidly to 0 as lag increases. Sample variance can be used to identify D value. Minimum sample variance will address the value D after differencing. Example 1. Let us consider an example of monthly RPI time series. ACF decayed slowly exponentially to 0 and their sample variance are var xt equals 0.698, var nabla xt equals 0.597, var nabla 2 xt equals 0.706. 6. Statistical applications in environmental sciences. One can see that sample variance after first difference is minimum. So D would be 1 for this time series. 3.2 Parameter estimation. After addressing the value of P and Q, next step is to find estimate parameter. There are several methods available in the literature to estimate parameter. Some of them are method of moments, maximum likelihood method and least square method. Least square method is widely used method to estimate parameter because it is a simple and easily solved method with easy mathematical calculation apart from biasedness. Least square method is used to estimate parameter alpha 1, alpha 2, alpha p and beta 1, beta 2, beta q for ARIMA P, Q model. The ARIMA P, Q model is given as yt equals n array summation alpha I yt minus I. P. I equals 1. Plus et plus n array summation beta j. Q. J equals 1. Et minus j. Where et are normally distributed error terms. Note, estimate of parameters using least square method and maximum likelihood method are equal when et are normally distributed. It is easy to estimate parameter by hand by using least square method for AR1 and MA1. When number of parameters are more in numbers like 20 or 30. It is very difficult to estimate parameter for AR20 or MA30 by hand. Similarly, it is also difficult to estimate parameters for a RIMA model. So, there is a need to use statistical software to estimate parameter easily or accurately for long run. There are many statistical software easily available for solving time series problem. Some of them are reviews, SAS, Python, R, SPSS, etc. An example will be solved using R that will help you to understand the topic in a clear manner. It will be helpful for you to understand estimation procedure using computer programming in practical scenario because real-life data is available for long time span. 7. Statistical applications in environmental sciences. 8. Statistical applications in environmental sciences. I. Three point three Diagnostic checking. After identification and estimation of the parameters, next step is to perform diagnostic checking. Diagnostic testing is used to inspect the parsimony ARMA model to the underlying time series process. If the parsimony ARMA P-Q model is a good approximation to the underlying time series process, the residuals process will form a good approximation to a white noise process. If the residuals ET will not form a good approximation to a white noise process, the process will repeat again. This process will repeat until residual process will be a good approximation of the underlying time series. There are several tests in the literature to diagnose it. Some of the most useful tests are 8. Statistical applications in environmental sciences. I. Inspection of the graph of ET. To check if residual process is a good approximation to a white noise process, plot the graph ET against T if this plot should not show any pattern. If the visual inspection of the graph of the residuals shows any pattern, this graph highlight a poor fitting model. This pattern effect is due to average level of the residuals or magnitude of the fluctuations about zero. This should be taken to mean. So that this ARMA model is inadequate and there is need to repeat the whole procedure again. E. Inspection of the sample ACF of ET. One is very much familiar with them of term ACF and PACF. There are many ACF and PACF values corresponding to underlying time series process. If these ACF or PACF values of the sequence of residuals are too many outside the range plus or minus 2 square root n, one can conclude that fitted model does not have enough parameter. So, respective time series model is not appropriate and repeat the whole process to get appropriate one. 4. Box-Jenkins step-by-step approach. The Box-Jenkins approach involves the following steps. 1. Calculate the ACF and PACF of the data, check whether the series is stationary or not. If the series are stationary, go to step 3, if not, go to step 2. 2. Take the logarithm and the first difference of the raw data and calculate the ACF and PACF for the first logarithmic difference series. 3. Examine the graphs of the ACF and PACF and determine which models would be good starting points. 4. Estimate parameters of the models. For each of these estimated models, check to see if the parameter of the lag is significant. If not, then you probably have too many parameters, and should decrease the order of P and or Q. 9. Statistical applications in environmental sciences. B. Check the ACF and PACF of the errors. If the model has at least enough parameters, then all error ACFs and PACFs will be significant. C. Check the AIC and BIC together with the AGR2 of the estimated models to detect which model is the parsimonious one. 5. If changes in the original model are needed, go to step 4. 5. Forecasting. Once time series process passed through the diagnostic checking, it is ready to go to next step, that is to forecast future value based on the estimated time series model like ARMA and ARIMA. Mostly estimated model will be ARMA model by Box-Jenkins method. Using Box-Jenkins approach, forecasting is relatively straightforward. Fitted an ARMA model to the data Z1, Z2. Cn, the equation is Cn plus K equals mu plus N area summation alpha I. P. I equals 1. Cn plus K. Q. J equals 1. En plus K minus J. The forecast value of Zn plus K given all observation up until time n, known as the K step ahead forecast and denoted Znk, is obtained from this equation by replacing all parameters by their estimated values. Replacing the random variable Z1, Z2, Cn by their observed values Z1, Z2, Cn. Replacing the random variables Zn plus 1, Zn plus 2, Cn plus K minus 1 by their forecast values. Cn1, Zn2, Cnk minus 1. Replacing the innovations E1, E2, En by E1, En. Replacing the random variables En plus 1, En plus K minus 1 by their expectations, 0. This forecasting is based on the past values and current values, so that it is the good method to forecast. In the following example, we will discuss about forecasting a RIMA process. 10. Statistical applications in environmental sciences. 15. For the best. 18. 18. Statistical application. 7. Summary. 7. Summary. The major assumption is that the underlying patterns in the time series will continue to stay the same as predicted in the model. A short-term forecasting model, say a couple of business quarters or a year, is usually a good idea to forecast with reasonable accuracy. A long-term model like the one above needs to be evaluated on a regular interval of time, say 6 months. The idea is to incorporate the new information available with the passage of time in the model. Box-Jenkins methodology is a good criterion to fit best model to any underlying time series and forecasting future values using standard statistical model like ARMA and ARIMA. One can apply available R code to other time series data. One can easily install and use R as an open source software. One easily download the setup for R from search engine or using the link given below. This module will help you in applying the Box-Jenkins on the real-life data. One can understand the importance of time series model, how to find appropriate model for the data that is used for future forecasting. 19.